Here we're going to be talking about how to translate from words into algebra. So for the most part, we're going to be talking about translating into an equation, and the equation is going to be a function. In general, a function is basically something that just passes the vertical line to us. It doesn't have any domain values that repeat with different range values, but here we're going to be talking about very specific types of functions that actually have an equation relating an x and a y to each other. Before we jump into that, we just have to talk about key math words. So we're going to talk about words that mean addition, subtraction, multiplication, division, and what really means the equal sign. And then we're going to actually practice with directly translating from a sentence to a function and actually back. And more, a little bit more in depth, we're actually going to be talking about how to go from a word problem all the way to a function, all the way to a graph of an equation. So before we get into all of that, we're just going to start out by defining our keywords. So anything in this list over here is going to be addition. So just an example of that could be x plus 3. So plus is an easy, simple word that means addition. We could also see the mathy word for that, which is sum. Sometimes you'll see it phrased in a word problem as combining or the total. And then we have these specific phrases that actually tell us to flip the order. If I say 3 is added to x, I'm actually starting with the 3. In the sentence, I say 3 first, but actually it comes second in the expression. Added to, or if I say more than. Both of those actually flip the order. If I say 3 more than a number, it's starting out with a number, and it's 3 more than that. The 3 actually comes second, even though in the actual sentence I say it first. And I could also say a number increased by 3. And when I'm talking about money, I'll usually talk about adding money as a deposit. For subtraction, I'm going to try to use the opposite words in the same spots. So the opposite of plus is minus. The mathy word for a subtraction problem is the difference. I'm going to try writing that again because it was kind of sloppy. When I say the difference between x and a number, it's happening in that order. The order that I say it, the difference between a number and 3 is going to be x minus 3. I could say in a word problem, you can see the phrase take away. And then we also have the phrase less than, which is the exact opposite of more than. But it does the exact same thing. If I say 3 less than a number, I'm saying I'm taking 3 away from a number. I start out with that number and I take away 3. It's 3 less than a number. It's happening in this one. I could also see decrease by. That does not flip the order. It's a number decreased by 3. And when I'm talking about money, oh, sorry, I have this one. Sorry, subtracted from. That actually is one that we're going to see flip the order. If I say 3 subtracted from a number, I start out with a number and it's 3 subtracted from that. The 3 actually happens after that. When I'm talking about money, I'm talking about withdrawing money. Sometimes you might also see deducting. So there's specific words in here that mean flip the order, and they only really deal with addition and subtraction when we see the words from, then, or to. From, then, to, that means we have to switch the order of whatever we see. So anytime we see from, then, or to, that means we're flipping the order of whatever's naturally written in the English sentence. For multiplication, we could just see multiply by. We can see the mathy word of product. We can see the really simple word of just times. Then we have specific ones. Multiplying by 2 is doubling something. Multiplying by 3 is tripling something. For example, if I say triple a number, that would be 3 times x. I could also see 1/2 of. Or let me write that a little bit smaller. I see 1/2 of or 1/3 of. That word of is actually telling us to multiply. That would look like this: 1/2 of a number is 1/2 times that number, or 1/3 times that number. We could also see phrases in a word problem that say per, each, or every. All of those mean the exact same thing. Per, each, or every. Those all mean multiplication. The problem is they can actually mean division also. They can also mean division. Kind of just depends on the sentence that you're seeing there. If I say, how many pieces of candy did you eat per hour? That's actually division. If I say you ate 6 pieces of candy per hour, and you want to find the total that you actually ate, that's multiplication. So it kind of depends on how those are used. We could also see just simpler ways of writing division, which is divided by, or the mathy way is quotient. Or I could split something evenly. Might also see that phrase a little bit differently. Actually, division seems to be the more fluid one that's used, but split evenly is a key phrase that you might see. So if I say a number is split evenly over 3 months, that means I'm dividing that number by 3. Equals is usually the most straightforward. Anytime you see the word is, or any form of the word is. So you can see are. You can see the future will be. You can see the past was. Any form of the word is. Sometimes you'll see total. And the mathy way to say equals is equivalent. So this should just basically be a word bank for you to use as you're going through these problems. Just check in on these and think about what those words really mean before you just commit to a expression. There's also different words that mean x and y. So sometimes it's going to be really straightforward. It's going to be x is 3 minus a number, or 3 minus x even. So sometimes they might just say the letter there. Other times they'll make it a little bit more coded. So the x, actually you learned this in science, and you definitely learned this last year, the x is the independent variable in a function. While the y is the dependent variable. The x can also be referred to as the input. It's the number that we're putting into the expression or equation, and we're getting an output. It's the input and the output. And the way we phrase these two things with functions, when we learned about whether it's a function or not, we talked about them as domain and the range. If you can't really remember these, the easiest way to remember these is that the x always goes into the equation, and we have an output for that. And the word in is in each of the vocab words for x. Alright, so we're going to write sentences for each of these examples. There's more than one correct answer, but I'm going to have you copy down these exact ones just so you can see an example of what this might look like. I'm going to write them sometimes in mathier ways, sometimes in really simple ways. I'm going to start off really simple. Y is 3 times x plus 1. There's more complicated ways that you could say that, but that is just the simplest way. Y is or equals 3 times that x plus 1. I'm going to get a little bit mathier with this one. The output, the output equals 5 less than the input. Remember, even though the 5 happens last in that equation, even though it's there really, in my sentence, when I say it as this, 5 less than something, I'm changing the order of that. I have my input first, my x comes first, and then I have the 5 less than that, which is really just subtracting from it. All right, on the next one, I'm going to say y equals twice a number subtracted from 5. And that might seem weird too, but when I have that phrase subtracted from, even though I say this twice a number first, it's actually happening second. I'm taking that away from the 5. I start out with 5, and then I subtract from that, I subtract 2x. All right, the range, or the y, is 1/2 of the domain minus 1. Again, there's a bunch of different ways that you could say these. I just want to give you certain examples. When you see that phrase 1/2 of, that's multiplication. It's 1/2 of the domain, or 1/2 times the domain. On the next one, I'm going to use input and output. The output is, and this one's a little bit tricky because we have a big fraction there, saying that's actually kind of specific. So I'm going to say, I'm going to use a mathy word here. The sum is, the sum of, we got to say input of the input and 9. So all I've said so far is the sum of the input and 9. That's the addition problem on top. And I want to have all of that divided by 4. Now, if I just say divided by 4 right then, I'm only saying that the 9 gets divided by 4, but that's actually not what I want to say. I want to say the whole thing gets divided by 4, so I'm going to put a comma there. That implies that everything that came before it, all of that is divided by 4. You need that comma to show that you're actually dividing the entire expression there. The whole sum gets divided by 4, not just the 9. It's really similar on the next one. I'm multiplying the entire x minus 2. It's all getting multiplied times 3. It's not just the x. So I'm going to say y equals 3 times I'm not going to use a comma here because that wouldn't really make a whole lot of sense in that sentence, but I'm going to group them in a different way. I'm going to group them the same way I group this. When you use those Matthew words, you're using a specific thing. It's either the sum or the difference, where you're using that whole thing. That entire thing needs to get multiplied by 3. I'm multiplying the entire thing times 3. It's 3 times the difference. It's 3 times the whole subtraction problem. It's not just multiplying x times 3, it's multiplying 3 times the entire subtraction problem inside of there. That's what I'm trying to say there. So I'm going to say 3 times the difference of x and 2. Right, I think going the other direction is a lot easier because there's basically just one right answer. You don't have to make up whatever you want for the sentence. And the way I want you to do this is actually labeling every step of the equation, every step of the sentence, every part of it, with whatever it's talking about. So you translate that directly on top of the sentence. I want to say y is equal to, I know that's going to be my equal sign, 6, so y is equal to 6 less than 1/3 of a number. When I see that phrase less than, I know it means subtraction. And then I have the phrase 1/3 of a number. That means I'm multiplying 1/3 times some number. I don't know what that number is, so I'm going to label that as x. Now I have that specific phrase in there that's telling me to flip these around. That phrase less than is saying I have to change the order of that. So y equals, that part stays the same. It's just the two things on opposite sides of that phrase. This thing, the 1/3 of a number, and the 6. Those things switch order. 1/3 of a number and 6. It's 6 less than 1/3 of a number. Next one says the product, the multiplication problem between 2 and a number, is decreased by 3, and that is y. You can write it in that order, or I'm going to actually flip it around. I'm going to put the y in front. Generally, when we see functions, we're going to see the y up front. We're going to see this in what we're going to call slope-intercept form. So we can write it in that order, or we can flip the order around. We can write in what we're going to see as slope-intercept form, where you see the y first, the y equals, and then the expression for x. That's 2x minus 3. Next one says the output, the y, is equal to, so the output is equal to 2 times the input, 2 times our x. That one's simple, y equals 2x. Next it says one more than is telling us to add more than the quotient of these two things. Whatever comes next, it's dividing those two things. It's the quotient between those two, which is x divided by 7, and that is 7. Sorry, that is y. I said that wrong. Now, I got a couple things going on there. Usually, when you see the quotient, we're going to see that as a fraction. So we're actually going to put the x over 7. We also have one of those switching phrases, more than. It's one more than that quotient. I'm going to put the y first again. That's not switching the order. That's just rearranging it just because I like seeing the y first. Y equals 1 more than the quotient of x and 7. And our last translating one, the independent variable, that's our x, is subtracted from 10, and that is the dependent variable, which is y. So again, I have to change the order of that. I see that phrase subtracted from. That means it's actually going to be 10 minus x. the independent variable, the x, is subtracted from the 10. I start out with 10, and then I subtract away that x. And that is the dependent variable, or that is y. Okay, so we're also going to see these, rather than just directly translating a sentence into an equation, we're going to see them in a word problem where you actually have to break down what that word problem is saying, pick out the key words, and write that as an equation. So Valentina's total monthly cell phone bill costs 10 cents per gigabyte used, and a flat fee of $45.60. Write an equation for the monthly cost, which is y, based on her gigabytes used, which is x. Now this is helpful because it actually tells us exactly what they want us to label the variables with. The total cost, the monthly cost, is that y. And in general, all of these equations are going to have the same form, at least for now. You're going to see this form where it's y equals some expression in terms of x. That's exactly what's happening here. It's 10 cents per gigabyte. It's times the number of gigabytes, which we don't know yet. That's the x. It's 10 cents times the number of gigabytes, which we don't know yet, plus that flat fee. A flat fee is just a one-time fee that we have to pay. We're paying a flat fee of $45.60. And that's it. All we have to do is translate that into an equation. And the next one says, Diego and his friends went to the movies. Tickets were $6 per person. They each received a $1.50 student discount. Write an equation to represent the cost of the tickets, y, based on the number of tickets, which is x. So notice I'm just highlighting the parts that have the numbers in them. Really, it's the phrase that goes around the number, $6 per person. They each receive a $1.50 student discount. Those are the key phrases there that are going to generate this equation. The total cost is our y, and that equals 6 per person, $6 times the number of tickets that we need to buy. But we're also getting a discount for each person. That's important. It's each person. So that's actually also going to be multiplication. It's $1.50 for each ticket that we buy. But a discount, actually that should have been one of the mathy money words. We're actually subtracting there. If we're getting a discount, we've just learned about this, that we subtract that amount. So we're subtracting $1.50 for each ticket that we buy. Then the next one says, Shahali buys 3 pairs of pants for $18.50. Sorry, they're $18.50 each. That's really important. They're $18.50 each. Actually, I'm just going to start with that. 3 pairs of pants for $18.50 each. There is no x in that part of it. Even though it says that phrase each, that word each, we're multiplying it, but we already know the number that we're multiplying by. We're buying 3 pairs of pants. And some number of shirts for $15.50 each. We don't know the number of shirts, so that we need to actually multiply by x plus $15.50 for each shirt that we buy. The number of shirts is our x, that's what I have labeled there. The total cost is our y, so this all equals y. That's the pants plus the shirts together, that equals our y. All right, the last one, there's 2 numbers. The larger of the 2 numbers is 9 more. The larger of the 2 numbers is 9 more than 1/4 of the smaller. Write an equation where x is the smaller one and y is the larger. Okay, so I'm just going to break this down. Actually, this is more of direct translating. The larger one, we're calling that y, is, that equals, y equals 9 more than, that's 9 that's being added to something, so I'm going to do plus 9 on the end of this, 1/4 of the smaller one, 1/4 of x. Okay, so all of that was building just so that we can get to basically this step where we're given a sentence, and now we can translate that sentence and graph that function. So really, this sentence is describing a function that we can put onto the graph. And the whole point of this, the graph, is an easy way to visualize what's actually happening in that sentence. All of these word problems, all these practical, real math problems can be solved and visualized with a graph. It tells us a lot more looking at a picture than looking at just a scattering of numbers. Or a sentence, actually. That's even the most vague way of seeing it. So first we have to translate it into an equation. Then we're going to make it into a table of points. And then from that table, we're going to graph it. So the output is 2 more than double the input. The output, that's our y. That is 2 more than double the input. That's 2 times our x. Our input is our x, so it's 2 times that. We do need to rearrange that order. We see that phrase more than. It's 2 more than something. So I'm going to flip the order of that. Y equals 2x plus 2. From there, I'm going to take that equation and plug in each of these x values. They're each going to go into that so that I can eventually graph some coordinates. When I plug in -1, it's -1 times 2 plus 2. -1 times 2 is -2 plus 2 is 0. So -1, 0 is one of the points on this line. When I plug in 0, 2 times 0 is just going to be 0, plus 2 is 2. The point 0, 2. And then I plug in 1, 2 times 1 is 2, plus 2 is 4. So 1, 4 is my third point on that line. Now I'm going to plot 1, 4, 1, 2, 3, 4, 0, 2, and -1, 0. If it doesn't form a straight line, something went wrong. Each of these, when you have an equation like that, it should form a straight line, like those two. Every time they should line up perfectly like that. And you want to graph at least 3 points on a line to confirm that you're getting a straight line. 2 points, don't draw this, but 2 points will always form a straight line. Those 2 blue points will automatically form a straight line. It doesn't matter if I graphed one of them wrong. That will still form a straight line. But when I do 3 of them, I can tell that those are not going to line up. So I must have done something wrong. Maybe it looked like that, and they actually do line up now. All right, on number 2, y equals the quotient of x and 2, so the division problem between x and 2, plus 1. So now I have my equation. I'm going to take that and use each of these x values in there to find my y values. I'm going to plug in -4. That gives me -2 plus 1 or -1. So -4, comma 1, sorry, -1 is one of my points. -4, -1 is a point on the line. I plug in 0, I get 0 plus 1, that's 1. So 0, 1 is another point. 0, 1 is my second point. Then I plug in 4, I get 2 plus 1, that's 3. So 4, 3 is my final point, and I want to make sure that those actually line up. 1, 2, 3, 4, 1, 2, 3. That looks good, but since I have a computer to help me, I want to make sure that those actually line up. Yep, that makes a perfectly straight line. All right, for each of these, I want you to graph them on your own, but I am going to translate them for you just to help you with setting up the equation first. the dependent variable, the y, oops, that actually made a y anyway. The y is -4 times the independent variable. We don't have to change the order of that. That is just y equals -4x. Y equals the difference of 2 and x. It's happening in that order. There's no switching words. It's just y equals the difference 2 minus x. Difference means subtracting, and it happens in that order. The dependent variable, or the y, is 3 less than 4 times the independent variable. 3 less than. That's one of those switching phrases. Less than is telling me I'm actually taking that 3 away from something. I start out with something, and then it's -3. And the thing that I start out with is this 4 times the independent variable, or 4 times the x. And the last one, the output, is the y is 3 times the sum. This is an important phrase, 3 times the sum. It's not just 3 times something, it's 3 times the addition problem. 3 times this. This is one thing, the sum of 1 and the input, times some addition problem, which is 1 and the input being added together. I'm going to write that a little bit cleaner in my next part. 3 times, really we're going to distribute there, times 1 plus x. The 1 plus x is the sum part. It's 3 times the entire sum. When you plug in these numbers, actually don't distribute. If you were to simplify this, you would distribute, but since we have numbers to plug in, you just follow PEMDAS, so you're going to do in the parentheses first, then multiplication. That's just a little bit easier. Alright, so go back and graph these 4 before you move on to anything else.